Now let's look at step 9, which is to check for intermediate panel BEFC. Check if the panel BEFC is governed by shear buckling. Calculating the shear buckling coefficient for panel BEFC. Panel BEFC is the adjacent panel to the previous panel that we did. Here we are increasing the spacing between the stiffeners from 2500 to 3250. So the C by D ratio becomes 3250 divided by 2600, which is equal to 1.25. When C by D is greater than 1.25, the shear buckling coefficient equation changes. So the equation now becomes 5.35 plus 4 divided by C by D the whole square for C by D greater than 1.0 as given on the right hand side, which is boxed in blue color. So we substitute the value of 1.25 here in this equation, so it becomes 7.91. Now let's check if D by TW greater than 67 epsilon into root of kV by 5.35 for web with stiffeners. Substituting epsilon equal to 1, kV equal to 7.91, we have D by TW equal to 2600 divided by 16, which is equal to 162.5. The other side is 67 epsilon into root of kV by 5.35, which boils down to 81.47. Obviously 162.5, which is D by TW, is greater than 67 epsilon into root of kV by 5.35, which is equal to 81.47. So the intermediate panel BEFC is now governed by shear buckling. Now let us calculate the shear buckling of the panel BEFC. Three components contribute to the shear strength of web V ultimate. The first is the primary buckling strength of plate due to elastic critical stress of the plate VCR. The second one is the tension field action of the web. The third one is the plastic moment capacity of the flanges. Now let's go step by step. Let's calculate V critical. Now let's calculate the primary buckling strength of the plate V critical. The critical buckling stress under shear tau critical E is given as kV into pi square E divided by 12 into 1 minus mu square into D by TW the whole square. Substituting E equal to 2 into 10 power 5 MPa, mu equal to 0.3, which is the Poisson's ratio for the plate. D by TW is the slenderness of the web, which is 162.5. The shear buckling coefficient, basically the elastic shear buckling coefficient, K sub V for the plate is 7.91, which we calculated in the previous step. We have tau critical E is 51.15 Newton per millimeter square. Now we have to calculate lambda sub W, which is the non-dimensional web slenderness ratio. Lambda sub W is given as root of FYW divided by root 3 into tau critical E, whose value is 250 into root 3 into 54.15, which gives rise to the value of 1.63. Now 1.63 is greater than 1.2, so we use the equation on the right hand side, which is the third equation highlighted in yellow color. When lambda sub W is greater than 1.2, tau sub B equal to FYW divided by root 3 into lambda W square. So when we do so, we get tau sub B equal to 54.33 Newton per millimeter square. So the shear force corresponding to the web buckling V critical equal to AV into tau B, which is 2600, which is the depth of the web plate into 16 thickness of the web plate gives you the area multiplied by the stress 54.33 gives you the shear load, which is 2260.13 kilonewton. Now the nominal shear strength Vn is equal to 2260.13 kilonewton. The design shear strength is Vn divided by gamma m naught, which is equal to 2260.13 divided by 1.1, which is equal to 2055 kilonewton. Now check if the shear buckling strength from the critical stress is adequate for the factored shear force at the stiffener BC. Now if you look at stiffener BC, it is not at the support, it is away from the support. Previously when we checked for ABCD, we checked for the reaction 2301, but here the shear force actually linearly varies because of the uniformly distributed load. So we have to check the shear force at the junction BC. So when we do so, we see that the factored shear BC is equal to 2301 minus 2.5 into 79.5. 79.5 is the UDL that is occurring, and 2.5 is basically 2.5 meters, which is the spacing between the support as well as the location of the stiffener BC. So that gives you the value 2102.25 kilonewton. Now therefore the factored shear 2102.25 kilonewton is greater than the design value 2055. So V critical is inadequate to resist the factored shear force, hence we need to take advantage of the post critical buckling strength of the web. Now then we have to come to points 2 and 3, which is the tension field action of the web and the plastic moment capacity of the flanges, both of which are given in the form of V sub T and V sub D need to be calculated as per IS 800 2007. The shear buckling strength due to tension field action V sub T is given on the right hand side of the slide. This is based on reference section 8.4.2.2 of IS 800 page 59. Now let's check if the tension field method can be applied to BFC. There is a criteria that we need to make sure that it is taken care of. The criteria is that the C by D, which is the stiffener spacing divided by the depth, should be greater than or equal to 1.0. So when we do so, the stiffener spacing is 3250, C by D is given as 1.25, which is greater than 1.0. Hence the tension field method can be adopted. Now the nominal shear resistance Vn is given as VTF, and VTF is given as AV into tau B plus 0.9 WTF into TW into FV into sin phi, which should be less than or equal to V sub P, which is the plastic shear capacity. Now we know that the first component AV into tau B is given as 2260.13, which we have already calculated in the previous slides. Basically, let us calculate the second component. Now finding the inclination of tension field, we know that the first and foremost thing is to find the phi value. The phi value is given as tan inverse d by c divided by 1.5. You can see that it is just tan inverse d by c in the code, but actually it is erroneous. The errata of the code actually says that it should be 2/3 of tan inverse d by c, or here it is written as tan inverse d by c divided by 1.5, which is the correct phi equation that we need to take into consideration. So when we calculate phi equal to 2/3 of tan inverse d by c, we have 2/3 of tan inverse 2600 divided by 3250, which gives rise to the value of 25.77. Now sin phi equal to 0.4348, cos phi equal to 0.9005, and sin 2 phi equal to 0.7831. Fv is given as Fyw the whole square minus 3 into tau sub b the whole square plus psi square the whole power 0.5 minus psi. Tau b is given as 54.33 Newton per millimeter square. The equation that we have written here is basically from IS 800, highlighted in the right side in the red color box. Here C is the spacing between the stiffeners, which is 3250 mm. The thickness of the flange T sub F equal to 50 mm. T sub W is the thickness of the web, which is equal to 16 mm. D equal to 2600 mm. And M equal to 20709 kilonewton meter. Sin phi is 0.4348. Cos phi equal to 0.9005 and sin 2 phi equal to 0.7831. Now psi is given as 1.5 tau b into sin 2 phi. So when we substitute that value, we get 63.82 Newton per millimeter square. Substituting the values in F sub v, we have F sub v equal to 176.43 Newton per millimeter square. Now finding WTF. WTF is basically the width of the tension field, and it is given by the equation on the right hand side. But however, the equation is erroneous because again there is an error due to printing when the code was printed. So the new equation or the correct equation is obtained from the errata, which is given as d cos phi minus of c minus s sub c minus s sub t into sin phi. WTF equal to the width of the tension field equal to d cos phi minus of c minus s sub c minus s sub t into sin phi. So substituting the values, we have 2600 into 0.9005 minus 3250 minus s sub c minus s sub t into sin phi. Now it boils down to finding the value of s sub c and s sub t. Now S sub c and S sub t is given by this equation, which is the anchorage lengths of the tension field along the compression and tension flange respectively, obtained from S equal to 2 by sin phi into MFR divided by Fyw into Tw the whole power 0.5, which should be less than or equal to the spacing C. Yes, we have to find out MFR, and MFR is the reduced plastic moment capacity, which is given as 0.25 B sub F into Tf square into Fyw into 1 minus Nf divided by Bf Tf Fyf divided by gamma m naught the whole square. And that equation is also given highlighted on the right hand side from IS 800. Now the axial force in the flanges N sub F is necessary to calculate MFR. So N sub F equal to M divided by D plus T sub F. Basically that is the distance between the two centroids of the flanges. Basically D plus T sub F is the center to center distance between the flanges, and it is given as 2600 plus 50. So NF equal to 20709 into 10 power 6 divided by 2650, which gives rise to the value 7.81 into 10 power 3 kilonewton. Now MFR is given as 0.25 into 780 into 50 square into 250 into 1 minus 7.81 into 10 power 6 divided by 780 into 50 into 250 divided by 1.1 the whole square. The value of MFR is now given as 27.3 kilonewton meter. Now we got the value of MFR. Substituting the above values into SC or ST, we have a C equal to ST equal to 2 divided by 0.4348 into 27.3 into 10 power 6 divided by 250 into 16 the whole power 0.5. So, we have the value of S sub C equal to S sub T equal to 380.01 millimeters, which is less than C equal to 3250 mm. Now, substituting the above values into WTF, we have WTF equal to D cos phi minus of C minus S sub C minus S sub T into sin phi. And when we do so, we have WTF is equal to 1258.65 mm. Now, we got WTF, we have FV, we have sin phi, we know what is TW. So, when we run the numbers into the above equation, we have 0.9 WTF into TW into FV into sin phi is given as 1391.32 kilonewton. So, VTF is equal to AV into tau B, which we have already found out, plus 0.9 into WTF into TW into FV into sin phi, which is given as 1391.32. So, 2260.13 is the critical shear buckling, which is AV into tau B, and the next component is 1391.32, which is the post buckling reserve capacity as a result of tension fail action. So, the total shear capacity is 3651.45 kilonewton. Now, the additional strength of web due to formation of tension field is 1391.32 kilonewton, which is beyond its critical shear buckling resistance of 2256.8 kilonewton. Although the critical shear buckling strength is less than the factored shear force in the panel, the shear buckling strength as a result of tension field action significantly contributed to the increase in overall shear buckling strength of the web. Now, let us look at step 10, which is to check for anchorage forces at end panels ABCD. The diagonal tensile stresses in the web create tension fields in the web panels. So far, the interior panels are balanced by the tension field of the neighboring panels, but in the case of end panel, it is clear that the panel is not balanced and it needs a support or anchorage at its left end. To maintain the end panel ABCD in balanced condition, the support is provided by the end stiffener. Besides the axial force, the end stiffener should also be designed for bearing moment produced by the tension field. We designed the end panel by simple post-critical method. While adopting this method, it is also necessary to check them for beam action of the end panel together with the stiffener spanning vertically between the top and bottom flanges. Basically, we have to understand that the end panel or the stiffener at the end panel will also be subjected to additional forces as a result of the unbalanced moment and shear forces. So, we have to check that as a beam spanning between the top flange as well as the bottom flange. So, the vertical beam so considered should be checked to resist the bending moment MTF and a longitudinal shear RTF. The end panel has to resist the tension anchorage forces RTF and MTF, which is given in the right hand side as per IS 800 anchorage forces, which is RTF and MTF. The resultant longitudinal shear RTF is given as HQ divided by 2 and the resultant moment MTF is given as HQ into D divided by 10. Where HQ is given as 1.25 into V sub P into 1 minus V critical by V sub P the whole power 0.5. Here VCR equal to AV into tau B, which is equal to D into TW into tau B. So, that is equal to 2600 into 16, which is the area of the web plate, into 67.16, which is tau sub B, which gives rise to the value of 2793.9 kilonewton. Now, Vp is given as D into TW into FYW divided by root 3, which is 2600 into 16 into 250 divided by root 3, whose value is 6004.4 kilonewton. Now, HQ is 1.25 into 6004.4 into 1 minus 2793.856 divided by 6004.442 the whole power 0.5. The value is 7328.6 kilonewton. Now, HQ here need not be reduced by the ratio V minus VCR divided by VTF minus VCR, simply because we have used simple post-critical method and we have not taken advantage of the post-buckling reserve strength for the panel ABCD, which is the first panel after the support. So, the resultant longitudinal shear RTF is equal to 7328.55 divided by 2, which is equal to 3664.275 kilonewton, and the design shear strength is Vp by gamma m naught, which is equal to 6004.442 divided by 1.1, which is equal to 5458.58 kilonewton, which is greater than RTF, which is the resultant longitudinal shear. Hence, it is okay. Now, let us also look at the resultant moment, which is 7328.55 into 2600 by 10, which is HQD by 10, which is equal to 1905.42 kilonewton meter. Now from flexure equation, the moment of resistance MQ is given as I by Y, which is the section modulus multiplied by the yield strength, and here we have to divide by gamma m naught because the partial material safety factor is required. So we have I equal to TW into C cube divided by 12, which is width into D cube by 12, and the width here is the thickness of the web. And if you can see here, the panel ABCD, the depth is 2500 because it is acting as a beam in this direction. The XX, it is bending about XX, and hence we have Y equal to C by 2. So when we run the numbers, we have 16 into 2500 the whole cube by 12, that is 20833.33 into 10 power 6 millimeter per 4, which is the moment of inertia, and Y equal to 1250, and hence we have MQ is given as 3787.89 kilonewton meter. Now which is greater than 1905.42 kilonewton meter, which is the resultant moment HQD divided by 10. So the resistance offered is greater than the applied moment. Hence the end panel is safe to carry the anchoring forces. Now let's go to step 11, which is the design of bearing stiffener AD. Calculating the dimensions of end post or bearing stiffener AD, maximum shear force is equal to the reaction, which is equal to 2301 kilonewton. So in addition to 2301, we should also calculate the resultant moment due to anchorage force MTF. So the bearing stiffener should also resist an additional compressive force because of the resultant moment MTF due to anchorage force. So when we do so, we have to divide the MTF with the spacing between the stiffness, which is 2500 mm. When we do so, we get a value of 762.169 kilonewton, which is the additional anchorage force. So the total design compressive force is 2301 plus 762.169, which is equal to 3063.169 kilonewton. Now let us find out the dimensions B sub S and TQ. Because it is an end stiffener, basically at the support location, you will not have the web on the left hand side, and so it resembles more like a T section if you look at it from the top flange view, and this is what you get. The stiffener width is B sub S and the thickness of the web is 16 mm. Now let's look at the bearing check as per IS 800. The area to be provided AQ of the stiffener in contact with the flange should be such that it is greater than 0.8 FC into gamma m naught divided by FYQ. 0.8 into 3063, which is the total design compressive force, into 10 power 3. Basically, we are changing from kilonewton to Newton, into 1.10, the safety factor, divided by FYQ, which is the yield stress of the stiffener, which is 250. So when we do so, we get 10,782.35 millimeter square. Now let's check for the outstand of the stiffener. Epsilon equal to 1.0 and B sub S should be less than 20 TQ epsilon, which is equal to 500 mm when we take the thickness of the bearing stiffener to be 25 mm, and B sub S should also be less than 14 TQ epsilon, which is equal to 350 mm. Now let's choose the length of the outstand B sub S equal to 230. So let us try two plates of 230 into 25 mm as a stiffener on either sides of the web as shown here. So the area provided is AQ equal to 2 into 230 into 25, which is equal to 11,500 millimeter square, which is greater than 10,782. Hence it is okay. Now let us check for buckling of end post or bearing stiffener AD. The buckling resistance P sub D is given as AE into FCD. The effective area is the full area or the core area of the stiffener together with an effective length of the web on either sides of the center line of the stiffeners, limited to 20 times the web thickness. Basically, when we are calculating the buckling resistance, the effective area can also include the web area on either sides of the stiffeners on the right side and the left side. The length is basically 20 times the thickness of the web. And here we do not have the web on either sides, we have only on the rightmost side. So we take 20 into 16 as the length of the web that needs to be taken into calculation. So the effective area is 2 into 25 into 230, which is the stiffener on either sides of the web, plus 20 into 16, which is the area, plus 20 into 16, which is the length of the web that needs to be taken into consideration, into 16 gives you the area. So the total area is 16620 millimeter square. Now let us take the moment of inertia about the center line of the web, which is Ix equal to 2 into 25 into 230 cube divided by 12 plus 25 into 230, which is the area, into h square, which is 230 by 2 plus 16 by 2 the whole square, plus you have the web that contributes, which is 20 into 16 cube divided by 12. So we have Ix equal to 224.788 into 10 power 6 millimeter power 4. Now let us calculate the radius of gyration about the axis parallel to the web. So Rx equal to root of Ix divided by Ae, which is equal to 224.788 into 10 power 6 divided by 16620. So the value is 116.3 millimeters. Now the flange is restrained against lateral deflection and rotation, and hence the effective length is taken as 0.7 times the length of the stiffener as per IS 800 shown on the right hand side in the highlighted form. Now the effective length is KL equal to 0.7 D. So we have 0.7 into 2600, which gives rise to the value of 1820 mm. Now the slenderness ratio lambda equal to KL by Rx, which is equal to 1820 divided by 116.3. We have 15.65 as the slenderness ratio. Now for lambda equal to 15.65, Fy equal to 250 Newton per millimeter square, and a buckling curve C. Why buckling curve C? Because if you see that for a solid cross section, IS 800 table 10 recommends a buckling curve of C. We have the value of stress FCD given as 225.31 from table 9C. So you can go to table 9C, we have to interpolate between 10 and 20. The lambda is 15.65. When we do so, we get FCD equal to 225.31, as you can see on the right hand side. So interpolating for 15.65, we have FCD equal to 224 plus 227 minus 224 divided by 20 minus 10 into 20 minus 15.65, which is 225.31 Newton per millimeter square. Now buckling resistance P sub D equal to AE into FCD, which is equal to 16620 into 225.31. So the value is 37446.6 kilonewton, which is greater than FC, which is 3064 kilonewton. Hence it is okay. Now let us check for local bearing capacity of the end post or bearing stiffener A sub D. So the bearing stiffeners is given by F sub W equal to B1 plus N2 into TW into FYW divided by gamma m naught. Now let us look at the cross section of the I section as well as the bearing support, which is given in the longitudinal direction. The thickness of the web is 50 mm. Now N sub 2 is defined as the length obtained by dispersion through the flange to the web junction at a slope of 1:2.5 to the plane of the flange. Assuming that the bearing support is 500 mm, when we do so, the N sub 2 is given as 2.5 into TF plus R. Here it is a welded plate girder, so the root radius will be 0. So we have to take N2 equal to 2.5 into T sub F, which is 2.5 into 50, which gives rise to the value of 125 mm. Dispersion will be on one side only. Why one side only? Because it is at the support. If it is a concentrated load at the top of the girder, it will be on either sides. So substituting the above values in F sub W, we have F sub W equal to 500 plus 125 into 16 into 250 divided by 1.1. The value is 2272.727 kilonewton. The load to be carried by the bearing stiffener alone is FC minus FW. FC is given as 3063 and FW is 2272. So the value is 790.44 kilonewton. Now the bearing capacity of the stiffener is two numbers into BS into TQ into FYQ divided by gamma m naught. Basically area into stress into 2. Basically 2 refers to two numbers of stiffeners on either sides of the web. Now this is given as 2 into 230 minus 15 into 25 into 250 divided by 1.1. Now what is this 15? Why are we reducing the width of the stiffener by 15 mm? We need to allow for a cope so that the web flange junction at that location, there is no issue with this welding that is taking place between the flange and the web. So you look at the figure that is shown on the right hand side, you have a top flange, you have a bottom flange, both of them are connected by the web, and there is a stiffener that is shown as a red color plate on either sides of the web. The plate actually is representing the bearing stiffener, but you also see that at the end of the plate closer to the web flange junction, there is a small area which is triangular. This area is basically the weld between the flange and the web, and hence there won't be a perfect fit at that location. The bearing is not done 100% by 230 mm. You have to reduce the area of the triangle basically to accommodate the presence of the weld that is happening at the web flange junction. So you have to reduce 230 by 15 mm. Right. So bottom is the plate girder, this is the end post of the load bearing stiffener, and you take a deeper look at it, you can see the triangle. This triangle is basically won't contribute to the bearing. So we have to take 230 minus the 15 mm. That is the actual area that contributes to the bearing. But the cope actually has a different meaning. I'm just going to show you a picture of what coping means in real world so that you understand better what is the meaning of coping. Coping is basically the connection between the two beams. When you have two beams that want to be at the same plane, there will be difficulty in the real estate. So you have to slightly cut the top portion of the web to allow it to make sure that the adjoining beam will come and join with the primary girder or the beam such that the top portion is flat, and the process of making it is called coping. So coping is something that I wanted to take an opportunity to tell you what coping is, but it has nothing to do with the current design that we are doing here. So we are not worried about the beam to beam connection here, but in general please understand, when somebody says coping, basically they are cutting a small portion of the top flange to accommodate the same level between the primary girder and the secondary beam. That is all coping means. Here in this case, we are just making sure that the bearing capacity is reduced by 15 mm. Right. Now let us come back. When we do the numbers, we have 2443.18 kilonewton, which is greater than Fc minus Fw, which is 790.44 kilonewton. Hence, okay. So we can adopt two plates of 230 into 25 mm as a bearing stiffener or end post on each side of the web. Let us look at step 12, which is the design of intermediate transverse stiffener B sub C. The check for minimum stiffener requirement is shown on the right hand side. So calculating the dimensions of intermediate transverse stiffener B sub C, the minimum moment of inertia required for the stiffener is based on the C by D ratio. So here the C by D ratio is 3250 divided by 2600, which is equal to 1.25. So 1.25 is basically lesser than root 2. So when C by D is less than root 2, which is 1.44, I sub S should be equal to or greater than 1.5 D cube into TW cube divided by C square. So 1.5 into 2600 cube into 16 cube divided by 3250 square gives rise to the value of 1022.36 into 10 power 4 millimeter power 4. Right. Now let us try two plates of 100 mm into 14 mm on each side of the web. The moment of inertia of the stiffener about the center line of the web is calculated by having this right hand side picture. Basically you have the stiffener and then you have the web on either sides. So the moment of inertia can be calculated by taking the thickness of the web. So the total depth now becomes 216, 100 plus 16 plus 100. So 14 into 216 cube by 12, 14 is the thickness of the stiffener, into 216 cube by 12 gives you the entire value, minus 14 into 16 cube by 12, which is basically you are subtracting the portion that is joining the two. Now we have 1175.25 into 10 power 4 millimeter per 4, which is greater than the required one, 1022.36 into 10 power 4 millimeter per 4. Now let us check for the outstand of the stiffener. The length of the outstand B sub S equal to 100 mm. B sub S is less than 20 TQ epsilon, which is equal to 280 mm. Here the thickness of the stiffener that is assumed is 14 mm. And B sub S is also less than 14 TQ epsilon, which is equal to 196 mm. Hence, it is okay. Now, let us look at the buckling check on intermediate transverse stiffeners. The stiffeners not subjected to external load and moment should be checked for a stiffener force Fq equal to V minus VCR by gamma m naught and should be less than or equal to F sub QD. So, from step 9, the shear at the stiffener BC is given as 2102.25 kilonewton. So, VCR is the minimum of the panel ABCD and BEFC from step 8 and step 9. So, the minimum of 2793.85 and 2256.8 kilonewton, we get a value of 2256.8 kilonewton as the VCR. So, FQ equal to 2102.25 minus 2258.6 divided by 1.1. So, this gives rise to the value of 50.613 kilonewton. Now, let us check for the buckling of the intermediate stiffener FQD equal to PD equal to AE into FCD. Now, here when we calculate the buckling of the intermediate stiffeners, we have to take the web into effect. So, 20 times into 16 basically is the length of the web that contributes to the buckling capacity of the intermediate transverse stiffener. This is different from what we did previously. We were doing some preliminary calculations to see whether the stiffener that is provided is sufficient and greater than the required one. But for buckling, we have to take into consideration the contribution from the web also, which is given as 20 times the thickness of the web on either sides of the stiffener. So, FQD equal to PD equal to AE into FCD, and the effective area A sub E equal to 2 into 14 into 100, which is the area of the stiffener. 2 is basically 2 stiffeners on either sides of the web, plus 2 into 20 into 16 basically is the contribution of the web on either sides of the stiffener. 2 represents the two numbers, 20 into 16 is the length of the web that contributes, multiplied by 16, which gives rise to the area. So, we have 13040 millimeter square is the effective area. So, let us calculate the moment of inertia about the center line of the web. So, we have Ix equal to 2 into 14 into 100 cube divided by 12 plus 14 into 100 into 100 by 2 plus 16 by 2 the whole square plus 2 into 20 into 16 into 16 cube divided by 12. So, we have Ix equal to 1197.09 into 10 power 4 millimeter power 4. So, we have the effective area, we have the moment of inertia. Let us calculate what should be the radius of gyration, but before we do so, we should also calculate what should be the curve that we need to take into consideration. This is a solid one, so as per table 10 of IS 800, we should take curve C. So, the radius of gyration here Rx equal to root of Ix by AE, which is equal to 1197.098 into 10 power 4 divided by 13040. We get a value of 30.29 mm as the radius of gyration. So, the effective length is scale equal to 0.7d. So, 0.7 into 2600, which is 1820 mm, which is also as per the codal provision. We did a similar exercise when we were calculating the buckling capacity for bearing stiffeners, where we showed the provisions in the code where it has to be taken as 0.7. So, the slenderness ratio lambda equal to KL by Rx, which is equal to 1820 divided by 30.29, we have 60.08. So, for lambda equal to 60.08, Fy equal to 250, and for a buckling curve C, we can look at table 9C. So, the design compressive stress FCD is given as the interpolation between 152 and 168. So, when we do so, we have a value of 167.872 Newton per millimeter square, and the buckling resistance PD equal to AE into FCD. So, 13040 into 167.82, we have 2189 kilonewton, which is actually greater than FQ, which is very small, 50.6 kilonewton. So, we can adopt two plates of 100 into 14 as stiffener on either sides of the web. So far, we have designed several elements of the plate girder. As you can see here, we have designed the flange plates, we have designed the web, we have designed the end post, we have also designed the intermediate transverse stiffener. One thing that we did not design here is the load bearing stiffener, which is very similar to the end post, except that in end post, we did not take into consideration the web on either sides, because the end post only one side of the web is taken into consideration while calculating the moment of inertia, whereas in load bearing stiffener the contribution will be on either sides of the web. So, that would be one change that we need to make, but the calculations remain more or less the same, and we have to check against the load that is taking place at the location. So, we have to take into account the shear force diagram and check for the load at the location of the bearing stiffener. So, two things need to be changed. We have to change the way in which we calculate the moment of inertia for the load bearing stiffener by taking the contribution on either sides of the web, and then we have to reduce the shear capacity from the shear force diagram at the location of the bearing stiffener and check for it. But it is an exercise that is very similar to the end post. So, for case of brevity, we have not doing that here, but you can understand that this is the only difference that we need to take into consideration. So, now let us look at the cross section of the plate girder at various locations. You can see that this is the plate girder, 780 mm is the width, thickness of the flange is 50 mm, and the depth of the web is 2600, and the thickness of the web is 16 mm. These are all drawn to scale, so you have a better understanding of the plate girder size and the dimensions. Now, at the end post, we have 230 mm as the width of the bearing stiffener, and the thickness of the bearing stiffener is 25 mm. And at intermediate transverse stiffeners, you can see that The width of the intermediate transverse stiffener is 100 mm and the thickness is 14 mm. Now, we may think that we have completed the designing of the plate girder, but what do you think? I think there is many things that we need to take into consideration. This is just preliminary sizing of the girders, and we have not completed the design unless we have completed the connections as well. Connections is a major thing that we have ignored in the design of the plate girders. So the answer is no. So the connection between the plate elements have to be taken into consideration. The first connection is between the flange and the web. So that would be a submerged arc welding that we need to calculate, and what is the thickness of the weld. So we need to take into account what is the shear that is acting at the location, basically the longitudinal shear, and calculate the required thickness of the web. And we should also determine the thickness of the bearing stiffener that is taking place at the web as well as at the flanges. And the next one, you should also calculate the thickness for the intermediate transverse stiffeners between the intermediate transverse stiffener and the web. Here we can closely see the welding between the top flange and the web as well as the bottom flange and the web on either sides of the web. Next is the bearing stiffener, and we can see the weld location of the bearing stiffener highlighted here, both on either sides of the web as well as the top and bottom flanges. So we cut a location of AA, we can see section AA which shows you the weld locations, and at section BB again it shows you the weld from the top flange view. We can see a cruciform cross section with welding on all four directions. Now the third one is welding at the intermediate transverse location. Here we don't weld to the top flange as well as the bottom flange. The only welding is with the web on either sides of the web. As you can see, when you do a cut section, you can see that the welding is taking place on the either sides of the web. Here also it is very similar to a cruciform cross section. The welding is done on all four edges or corners. We should also look at the connection between the two plate girders. The connections can be done by welded or bolted. Here we are highlighting the bolted splice connection because it is very difficult to transport the girders. The road width in India is basically very small compared to most Western nations. Length of the truck is limited to 20 feet to 40 feet. So that's the maximum length of the girder that can be transported. Because the width of the road is very small, it will be very difficult for the truck to maneuver and take the girders to the specified location. Hence, it is very, very important that we splice the girders, but also splicing is an art. We need to know exactly where to splice the girders because we don't have to put the splicing at the location where there is maximum moment. So the splicing has to be identified not only with respect to the transportation requirements, but also with regard to the design considerations. So the splicing has to be judiciously decided based on both the transportation requirement as well as the structural analysis requirement. Typically, it is spliced where the moment is very low and shear also very low. And here we are just showing one splice connection which is at the top flange as well as the bottom flange and at the web location. So a cross section view of the splices is shown here. You can see that the bolts that are running between the top flange and the splice plates at the top as well as the bottom of the top flange, and in the web you can see on either sides of the web you can put a splice plate. Similarly at the bottom flange, which is very similar to the top flange, where you have a splice at the top of the bottom flange, a splice at the bottom of the bottom flange. Both of them are connected by bolts. In addition to that, we should also consider the possibility of installing cross frames. Sometimes girders need to be lifted as one piece for stability reasons, and hence it becomes very essential to provide the cross frames at the ground before it is lifted and put in place. So the location of the cross frame should also be decided in advance. The cross frames are the ones that provide lateral stability to the girders. Typically the cross frames should be placed at every 20 feet. It should not exceed 20 feet because more than 20 feet there is a good possibility that the cross frames will have wobbling effect and it may undergo lateral torsional buckling. Basically cross frames are X-type bracings, as you can see on the picture. On top of that, we also need to consider the composite action. Basically the steel concrete composite deck also comes into picture. So we need to put the shear studs on top of the compression flanges to take advantage of the composite action. As you can see that on the picture, there is a small protrusion that is taking place on top of the corrugated deck. The corrugated deck are basically used to pour the concrete and as well as to remain in place. So it acts both as a formwork as well as a part of a structural component. The deck is basically a cold form steel whose thickness typically varies from 0.9 mm to 1.1 or 1.2 mm depending upon the requirements. And on top of it, then you put the shear studs with the help of a shear stud gun. And you can see the typical plate girder here is shown on the right hand side. The thickness of the compression flange here is given as 50 mm and the width of the compression flange is shown as 70 mm, but this can be further reduced due to composite actions. What we have solved in the class is basically a very ideal situation where the top flange and the bottom flange are the same in width and thickness, but in reality it need not be the same, because once the concrete is poured and the composite action is achieved, there is very less need to have a higher thickness and width of the steel plate. So to optimize it further, most people will take advantage of the composite actions and hence reduce the width and thickness of the compression flange for cost savings. So this is also something that we need to take into consideration. So the design of the plate girders is very large subject. What we have done is to give a glimpse of how the design can be carried out in a classroom setting, but when you go to real life, you will quickly understand that there is much more things that need to be learned while you design the plate girders. With this one, I would like to say thank you to you and then look forward to the next lecture.